Okay, so now we're going to carry out the second step here. Just as a reminder, this was a charged wire. So now what is our second step? Well, remember this is an electric field vector, and we are describing this in terms of its differential parts. So we see over here that if we remind ourselves that E as a vector is k times q over r squared r hat, we can likewise write this as dE is equal to k dq over r squared r hat. So one was the total electric field, the other part is just a small part of it, and we are writing this in terms of a differential equation. So I'm going to move this over to the side now and just write out our second step that we have to do here. So the second step is to set up your differential equations. So let's go back over to what we wrote before here in blue. Here's our differential electric field. Here's our dq. As a differential equation, you might be familiar with this form. But we want to integrate this to get the final electric field, which is why we're going to write this in this form. So let's go back to our example over here. Remember, electric field is a vector, so we have to break this into its components. So we see this will be dEx if I designate this as the x-axis, and this will be dEy if I designate the vertical as the y-axis. So now, following this, it's pretty easy now to describe our electric field. So here we go. Just going to move up a bit. We see for our first equation, dEy is going to equal to k dq over, and if I consider here that I have a right triangle here, I see that this leg is a, this leg is a over 2. Therefore, this distance from the charge to my point in space is, I should probably write this bigger, is L over 2 squared plus a squared, square root. So I can write that distance down over here as L over 2 squared plus a squared, and it's going to be squared, so I don't have to include the square root here. But remember, this is just a y component, so if I go back to my picture again here and I take this triangle here out of context, or in other words, I see that this is dE, I see that this is dE in the x, and this is dE in the y. If I just translate the y component vector over to form another right triangle, I see that this arbitrary angle I call theta here also pops up over here. So I can just as well write this as sine theta. Hopefully from watching the other videos you'll understand this quite easily now, why it's just sine theta. Likewise, for dE in the x, I can write this as k dq over L over 2 squared plus a squared times cosine of theta. Now, if I don't really know what the angle is, I just remember, what are trigonometric functions? They're just ratios of a triangle's side lengths. So now here, I'm going to rewrite this sine theta as a over the hypotenuse length. So k dq over L over 2 squared plus a squared, and then rewriting sine theta as a over the square root of L over 2 squared plus a squared. And I can just as well do the same for cosine as well. I get k dq over L over 2 squared plus a squared. Multiply that by L over 2 multiplied by that hypotenuse in the denominator, L over 2 squared plus a squared. Okay, this looks kind of messy, but we can reduce this, make this look nice. The radical is the same as taking the same term over here to the half power. That same term here is taken to the first power. So we can rewrite all of this in a much neater way as follows. So here we go. I can then say dEy is equal to Ka dq divided by L over 2 squared plus a squared to the 3/2 power. Similarly, I see for the x component, this will be k times L dq over 2 multiplied by L over 2 squared plus a squared to the 3/2 power. And now we've done the most important part. We have our two differential equations to describe the electric field. So we'll move on to the next step in the next video.